Whew, all right. Last problem. Thank goodness. So this is part three of the exam one, part C. So part C says if a positive test charge, so I drew that here, this positive test charge, Q sub naught. I guess I'll draw the sub naught part there. Whatever. Yeah, it's fine. Was placed in the region between A and B. So basically, I just decided arbitrarily to put it right there because that's in between that region. Derive an expression for the electric force exerted on the test charge in terms of the given quantities and fundamental constants. Specify the direction in your expression with a unit vector. Based on your result, does the conducting shell have any influence on the force exerted on Q naught? Explain your reasoning. So, if you remember from the previous problem, the electric field we got for that area, the electric field that we derived, was equal to, what was it? I know I have it somewhere. There it is. It's, the electric field was equal to 2q over 4 pi r squared epsilon naught. Epsilon naught. Yeah. This is a 2q. For that region. Yes. Cool. It's good. So now it wants us to derive an expression for the electric force. Well, we know that electric force is equal to the electric field times the test charge. This equation came from that the electric field is equal to the force felt by the test charge over the test charge. And so just to pretty much solve for force, I just need to multiply by the test charge here. And so that's how I get that. So by replacing, basically, to derive the expression, we just need to substitute this for E. So we get we can put a positive 2q over 4 pi r squared epsilon naught. And we would just need to multiply that by q sub naught, which is our charge, the point charge. And that's what the force is equal to. Yeah, that's it. Oh, well, and then it asks, what's the direction? Well, the direction here, so we need to know what the direction is. Well, the force is felt by the positive test charge on this, by this positive insulating sphere. So because they're both positive, it's going to point outward. And so remember, though, it's talking about any point inside here, not just this one. And so if we had a point up here, it would also point outward. And so the way to write that is just to say, for the direction, you can write radially outward. We can't say left, right, or because, here we could say it points right, but if the point was over here, it'd point up. Or here, it'd be point down. So we really just have to say radially outward as the direction. Now, it says, based on your result, does the conducting shell have any influence on the force exerted on? So there's a couple ways you can do this. One, if you remember, the forces from the ring would end up canceling out. And so from this portion of the ring, we would get a force pulling it this way. But then over here, we get a force pulling it this way. And so those forces would cancel out. Now, you would say, hey, the X components would then pull it that way. But notice that we have a portion of the ring here that would pull it this way. And it's closer, so it would be a stronger, or it would end up being, now we would get that around the ring. And so the outer shell has no effect on the, let's see, based on results can shell have any influence on the force exerted. So yeah, it would the forces outside of the insulating shell would cancel due to this being uniform. So it would and actually to prove it, if you take a look at your equation, there is no we're only accounting for the charge inside. Right? The force is only dependent on the force that's inside here. Nothing to do. I mean, we could draw our Gaussian surface too. If you just draw your Gaussian surface, the electric field is dependent only on what's inside, not outside. And we know that electric field helps electric field. We know that it comes. We know that the electric field causes the force, and if the electric field has nothing to do with the outside here, it only has to do with the inside, then we know that, yeah, we're only dealing with the force dealt with the insulating sphere, not the conductural sphere. Okay, cool. Hopefully that helped. Yeah. Good luck, y'all. Catch you on the flippity flip.